So let's talk about naming esters and their properties. When naming esters, I find that the easiest way to do this is to circle each side of the oxygen in the middle of the chain. So the oxygen in the middle of the chain, in this case, this oxygen right here, breaks the chain up into two pieces. I can then circle each side of the carbon chain that extends out from either end. So on the left-hand side, I have this large chain with the C double bond O, and on the right-hand side, I have a single carbon. Now, another thing you can do, and I find it helpful, is to place a small dot where each carbon is on these skeletal structures. My students oftentimes tell me that it's easier to see the carbons when they are labeled like that with the dot. Okay, so now we're going to number this chain. The 1, 2, 3, 4, and 5 carbons. So now 5-carbon alkane would typically be called pentane. But because this is a ester, it's going to get the ending 08. Now the side that gets the 08 ending is the more important side, the one with the double bond O here. The less important side is simply going to be named as though it were a branch. So this is a 1-carbon branch. That would just be called methyl. And then for writing down the full name for this compound, I put the less important side first, methyl, and then I put a space, and then I put the more important side, its name, which is pentanoate. So this would be methyl pentanoate. Looking at our next structure, we actually end up doing the same thing. We'll look for the oxygen in the middle of the chain, and then go ahead and circle either side of that oxygen. So the chain on the right-hand side, in this case, will be the more important one because it has the double bond O. Note that the more important side is not always the left side. Sometimes it's the right, sometimes it's the left. The more important side will be the one that has the double bond O. Okay, so I will number my longest carbon chain here, starting from the side closest to the oxygen in the middle of the chain. So this will be 1, 2, 3, and 4. And in this case, there's a branch off of that more important chain. And I'm going to go ahead and circle the chain here. I'll also go ahead and put my dots on the chain, representing the carbons. And that odd little group that's not part of the longest chain, that's actually going to be a branch. So I'm actually going to have a branch off my more important side. If I look at my less important side, you'll see a benzene ring with a bromine attached to it. Well, that benzene ring is the less important side's main chain. And I would start numbering that from where it is connected to the oxygen. So this would be 1, and I would go in the direction towards the branch off of that less important side, in other words, the bromine. So I'd number it like this. And of course, the bromine is a branch off of that less important side. So now we have our two pieces. We can go ahead and label the two pieces. The right-hand side, the more important side, it has a methyl group, and the methyl group is off carbon number 3. So I'll start with 3-methyl. But it also has, the main chain is 4 carbons. And so that'll be butan O8. Notice it gets the O8 ending because it has the double bond O, and it's the more important side. The less important side, the one without the double bond O, that's a benzene ring, but a benzene ring, remember the less important side gets named as a substituent, so benzene ring as a substituent is simply called a phenyl group. A phenyl group. However, you'll notice that there's a bromo group attached to the less important side, the phenyl group. So I'm going to actually call this 3-bromophenyl. 3-bromophenyl. So when I name this compound as a whole, I will call it 3-bromophenyl space 3-methyl butanoate. And that's the name of that compound. And you likely will not get anything quite that complex. Let's take a look at one more. If you have the benzene ring directly attached to the double bond O, as in this case, it actually gets a special name. So once again, I'm going to start naming this by circling both sides of that middle oxygen. The carbon chain that has the double bond O is the more important side. When the carbonyl on the more important side is directly connected to a benzene ring, we can simply call this benzoate. So benzoate. Now the less important side here, the 2 carbons side with no double bond O, is just going to be called ethyl, a 2 carbon branch. So then the name of this compound would simply be ethyl benzoate. Let's go ahead and take a look at some of the other properties of esters. Esters are actually much less polar than alcohols and carboxylic acids, and there is a reason for this. If you look at an alcohol has an OH bond, as well as a CaO bond. Well, the oxygen-hydrogen bond is actually much more polar than the carbon-oxygen bond. So you have a much stronger dipole moment with an OH bond than a carbon-hydrogen bond. In addition, an OH bond allows for hydrogen bonding. NH, OH, or FH bonds allow for hydrogen bonding. Esters, however, do not have any of that. The structure for an ester is always a carbon double bonded to an oxygen, single bonded to an oxygen, that's bonded to another carbon. So because there's no OH bonds in an ester, you end up with no hydrogen bonding, and that actually makes it considerably less polar than alcohols and carboxylic acids. There's also going to be a carbon chain present on both sides of the oxygen, and that can also contribute to the nonpolar nature of an ester, or rather, the less polar nature of an ester, because an ester is still polar. When we compare an ester to a carboxylic acids have both the C double bond O and an OH. So it has hydrogen bonding, but not only that, if you have 2 carboxylic acid molecules together, they will dimerize because they form 2 very strong hydrogen bonding interactions between, I'll draw it out here, between the hydrogen and the oxygen of the carbonyl here, and between this hydrogen and the oxygen of the carbonyl here. And those strong hydrogen bonding interactions greatly increases the intermolecular forces of carboxylic acids. So not only are carboxylic acids more polar than esters, and not only are alcohols more polar than esters, since esters have weaker intermolecular forces, esters have lower boiling points and melting points than alcohols or carboxylic acids of similar size. In fact, the size of an ester can even be a little bit bigger, and it will still have lower melting points and boiling points, just because of the much weaker intermolecular forces compared with the hydrogen bonding of carboxylic acids and alcohols. One cool thing that esters do is they can polymerize. If you have a dicarboxylic acid or a diester react with ethylene glycol, which is a diol, you can have a continuous reaction here where it forms a long chain of ester bonds, and this is called a polyester. Polyester, of course, as you know, is one of those things that can be used as a clothes fabric. In addition, 3-carbon alcohol like glycerol combines with fatty acid chains, which are long chain carboxylic acids, and they will form a fat or a triglyceride. So the triglycerides you see here have ester bonds that hold them together. So you'll see 3 ester bonds in this triglyceride. And one last fun fact about esters is that they smell really good. In most cases, they smell really good. So esters are responsible for the smells of raspberries, pears, bananas, apples, and other fruits as well, and also like vanilla. In fact, esters are used to make artificial flavors in those terrible for us but oh so tasty candies. So that's just a little bit about the properties of esters and how to name them.